discussion, we can still keep discussion on Slack. So feel free to post. And actually, we start the next session now. And after 3 talks, including online one, we have a lunch break. So yeah, the next speaker is our invited speaker, Kazumi Kashiyama from Tohoku University, Japan.
Okay, thank you very much. So, thank you very much for Hashimoto-san and everyone here for the organization. And today I'd like to talk about, actually it's really I'm also highly motivated by that discovery, very game-changing discovery of the global cluster, FRB, and one of the most actively debated topic about FRB sources. And I mainly talk about the accretion, merger-induced collapse of byKazumi. So here's the contents, and maybe I don't need to explain a lot about number one. I mean, the FRB have been discovered, recently discovered non-active stuff-forming regions, and I will briefly overview this point, and after that, one of the promising channel to form such kind of, well, still people believe that a good fraction of FRB is coming from some sort of neutron stars, and the discovery of FRBs from old system means that we have to make a young or some sort of neutron star in that kind of young system, old system. And one of the promising channel people believe is that accretion merger-induced collapse. And I will again also briefly review what's that process. And lastly, I would like to mention about the possible way of testing the connection between FRB and accretion merger-induced collapse of byKazumi. And actually, there are also, not from FRB radio observation side, we also have a new injection from time domain astronomy in optical, especially supernova search and also optical photometric search of the galactic objects. We have new injection about this context, so I would like to mention about that. So, as we heard, so again, I'll briefly go through the observational information about the FRB in non-star-forming region. Of course, most straightforward and robust detection is FRB 2020120E in M81 globular cluster. And as already discussed intensively, this is kind of game changer. So we discovered, although this FRB is still not conventional cosmological FRB, but still we have a very bright coherent radio emission from globular cluster system. And also, as for the so-called second repeat, this one is localized. Again, thanks for the nice localization of the source. We now identify where they are located. And actually, this source is also a little bit off from the nearest star-forming region. And that is also indicating that this one is also, the host system of this object is also not so young. But still, this one, well, Again, this is a very coherent, bright, coherent emission, so people believe still we need a neutron star, and we need a way to form such kind of objects. And these two localized events are very straightforward information. We can judge whether this is hosted in active star-forming region or so. But we also have indirect information, relatively indirect information about, for example, FRB host galaxies. So, although some of, for example, fast repeaters are in crazily star-forming dwarf galaxy, but some of the other cases are hosted in a non-star-forming, not so intensely star-forming galaxy, which may also indicate, well, like Uri-san proposed, maybe in principle most of the, or a good fraction of the FRB is coming from globular cluster system in these host galaxies. We will know if we have a millisecond localization of all of the FRBs. And again, relatively indirect information about the sources is that, for example, people check the offsets in the host galaxies, and group these. Oh, can I show point? Okay, I'll leave it. Okay. Anyway, so. You can discuss about offset and say this is consistent is not consistent with a non-stellar object like low mass X-ray binaries or pulsars or magnetars, and this kind of information can be also useful for judging what's the progenitor system forming FRB emitting neutron star. Again, here in this talk, I assume that the FRB is still coming from some sort of neutron star. Of course, it's not guaranteed, but that's kind of working assumption here. And another slightly rather indirect information is about the FRB population with respect to redshift. Although we only have handful numbers of redshift identified FRB, but we can use dispersion measure to discuss about the approximate redshift, and then discuss the distribution redshift, and then whether or not that's consistent with a star forming type or the accumulated stellar history type. For example, this one, you can look at the green one and purple one. Green one indicates the accumulated model, which means the accumulation of the stellar activity. For example, some sort of merger of the compact objects. On the other hand, purple one is a star forming history model, which basically tracing the star forming history in the universe. And the point here by these authors is that single population cannot explain the observed population that is indicated by red and orange. So they say that the mixture of these star forming population and accumulated star formation population is so far the best fit model, and which may indicate that like in the case of type 1a supernova, we have type 1a supernova and cooperative supernova. Like in the case of GRB, we have long gamma bursts and short gamma bursts. Both cases we have old population and young population, and this might be also the case for the FRB that start being informed from this kind of observation. And that's the probably, as all of you know, the current situation about the kind of information about the FRB source. And then again, the most straightforward information is the discovery of FRB from globular cluster system, and that kind of observation triggered intensive research about, I guess, young neutron star formation in this kind of system. And the idea is to collapse white dwarfs. Since globular clusters, we have a lot of white dwarfs, especially in the case of relatively big globular cluster, massive white dwarfs sinking down to the central region by the mass segregation, and where we have plenty of massive white dwarfs. And why massive white dwarf is important is that if you have a heavy oxygen neon white dwarfs, not carbon oxygen is more flammable. So as you hear from the type 1a context, the carbon oxygen white dwarf is more dangerous to be explored. But if you have oxygen neon white dwarfs, and if you succeed to accumulate matter onto oxygen neon white dwarfs, then the theoretical calculation in the say almost 80s. So it's 30 or 40 years ago, people theoretically proposed that in that kind of occasion, oxygen neon core not explode, but instead collapse into neutron star. So first thing happen is the electron capture by the magnesium and so on. Even though that, this is a central density, and so it corresponds to the time. So mass keep on accreting to the oxygen neon core, and at some point electron capture happens and some sort of heat is generated, but this is not turned into the detonation, just the convection is induced, and keep on mixing, they keep on burning, and more oxygen ashes are accumulated, and eventually that kind of Onemag degenerate core turn into the collapse into neutron star. That is shown by these theoretical calculation. So basically, this is how people believe accretion induced collapse. So kind of way to form young neutron star in all systems. General channel is to form massive oxygen white dwarfs and make matter accreted.
Has anybody observed this?
No, that's the point from here. Yeah.
But why not?
Yeah, that's the point from here. Yes. So, and then the question is how to make massive world with accreting mass. And actually, we have plenty of opportunity to have this kind of occasion. One way is to make gas accretes, form massive oxygen neon white dwarf and gas accretes. And the other way is to merge two white dwarfs, for example, oxygen neon and carbon oxygen. And then oxygen neon white dwarfs is enveloped with some sort of unburned ashes and keep on accumulating mass. And these two independent channels, so-called accretion induced graphs and minor induced graphs. And so actually we have a pathway to make this happen, but the point is we haven't observed, how to say, direct information, direct evidence of whether this happens. Yeah, that's I guess a problem in this context and also FRB context. Or problem, not an interesting point. And still we have theory and we have some candidate objects, so people have been speculated this kind of AIC, MIC system have been observed. For example, Kakani and Ryan paper in they say after the theoretical proposition of the accretion in the graphs, they also on the observation side people start to discover an interesting neutron star system like a subpopulation of low mass X-ray binaries and relatively young parcel system in global cluster. That's something like similar to the FRB in the M81. So for those kind of how to say, not so conventional neutron star populations in the relatively older system, people have been claimed that MIC or AIC can explain them. And I think that in this context, FRB source in M81 global cluster is kind of new direction or new input. So, so getting back to the question, so these, for example, subpopulation of millisecond pulsars or relatively young electric neutron stars in global cluster is a kind of less strange. I mean, still somewhat strange, but not totally strange compared with the conventional neutron star sequence. But on the other hand, FRB is still people believe much more strange than the conventional neutron star. So if let's say if all of these not how to say unconventional, relatively young system in the older stellar system is coming from AIC and MIC, then that indicates that there is a kind of variety of neutron star that can be formed from AIC and MIC. And the question is, what is the possible origin of that diversity, and what kind of physical properties are important to form FRB emitting neutron star by AIC and MIC is, I think, a question right now. Again, believing FRB is coming from neutron star and all the sources of neutron stars are formed by AIC and MIC is a working assumption. But I think it's a worth checking assumption. So that's, I guess, the very rough wrap up of the current understanding about the FRBs and also AIC and MIC in the FRB context. And the question is how to test the connection. And for example, for the MI81 system, Kramer and Lewis and so on, these people have done a nice work to how to test the AIC MIC scenario in the global cluster. For example, you should check these papers. It's really nice papers, and they one by one propose offset from host cluster, intercluster FRB repeaters, or red versus cluster blue cluster populations, and also cosmological rate distribution. This kind of information can be used to test the AIC MIC model for the globular cluster system in particular. But again, like Woody-san already pointed out, why we haven't seen this? Because we have a bunch of channels, and this globular cluster system is a very peculiar example. So question is more broad, more general sense, and I think how to say, connected with various astrophysical branches. So there are several missing links. So we know that the massive oxygen neon white was a kind of promising source to make AIC and MIC, and where and how many are they? That's a question. And oxygen neon white dwarfs is also, well, you may think that it's easy to identify oxygen neon white dwarfs, but it's actually not. And we don't, although, so that still we have to quantify. If you want to connect these channels to the FRB population, we have to quantify where and how many are there. And also, in the context of FRB, it's important to answer how strong magnetized and how fast it's rotating. So these pre-collapsing of oxygen neon white dwarfs. That's also very, very important information. But again, we have very limited information, knowledge about that. And next question is, like Kuri-san already asked, how that supernova explosion looks like. So if you say that these kind of channels in forming the kind of strange type of young neutron stars in old system, then why we haven't seen any, and why we have no smoking gun signature? So to answer that question, from the theoretical side, we have to model the, for example, light curve and so on, and discuss the detectability. And of course, in the FRB context, the important thing is after forming that kind of neutron star, whether or not that kind of neutron star can produce FRB is another question. But that's, I guess, more or less related to the emission mechanism topic. So I will ask other speakers in this session about the emission mechanism. I will mainly touch about the first and second point. From now on, I would like to list up several very recent observational and theoretical inputs about the first and second point. So this is still unpublished result, but we recently discovered a very interesting the so-called dwarf nova system. Dwarf nova system is a white dwarf plus Roman stars and gas accretions. And what we discovered is a very strange, very interesting spectral feature in X-ray band. What we discovered is that this nova system, this nova system is has been an intensive follow-up observation because this one was originally identified as ice cube counterpart. So ice cube detected neutrino, and the optical people discovered some transients. So originally they thought that this might be optical counterpart, so there are intensive optical multi-wavelength follow-up. So thanks to that kind of background, we have a kind of relatively better spectral information compared with other nova system. And this spectrum consists of black body here and oxygen neon lines here. So although the spectral resolution not so super nice, so still that each line has not been separated, but we can say this is oxygen neon lines. So the bottom line is this accreting system has a strong oxygen neon line. So it sounds like the center of white was oxygen neon. And the other important thing is we also detected black body component. So that you can naively, although it's kind of model dependent argument, but once we see the black body component, we can estimate the size of the system. And from that, we have a theoretical connection between the size and mass of the white dwarf. So from that, mass of these objects implied to be very heavy, like 1.24 or 1.36, and the companion mass would be roughly 0.1 solons or so. So if that accretion keep on going with another giga year, then this system might be one possible candidate of accretion in this collapsing system. And again, since as I said, that you may think this kind of system being discovered lots, but this is, as far as I know, one of the first examples of both detecting the oxygen neon signature and the massiveness of the system. And from that, we can see only one system, but we can roughly estimate the event rate. If you believe this system evolved into an AIC system, then the formation rate is like 10 to minus 6 per year per galaxy, and which may account for a fraction of strange type of neutron star system in all stellar population. But the point here, in the context of FRB, this point from the spectral information looks like don't have a strong magnetic field, since there is no polar channel flow information and so on. So it seems like the magnetic field is very weak. So if you just simply assume a flux conservation and so on, this system should evolve into something like millisecond pulse, not strongly magnetized, but rapidly rotating case. And maybe it's not so good for FRB. And this can account for channel for explaining classical AIC, MIC progenitor system, but maybe not so plausible for FRB source. And as for FRB source, we also have this kind of interesting system, which was also recently discovered by the Mount Wavelength observation. This system is actually a kind of infrared nebula system. But after the Gaia and localized position and intensive follow-up spectroscopic observation, people identify crazy type of oxygen neon emission lines. And but again, oxygen neon, so probably the central object will be oxygen neon white dwarfs. But the other crazy point is the mass loss rate and the expansion velocities are very, very high. Like this is still a white dwarf, but the mass loss rate is as large as massive star. and the expansion velocity of the wind is roughly 10% of the speed of light. That's very crazy system, crazy or interesting system. And
How do you know this not on Tech 1A? Like, how do you know that any of these not on Tech 1A?
that's another point. I will touch that point later. So, and so since we have current information from temperature and so on, we can argue that how this object will form and so on. Actually, by ourselves, people discuss about what's the central mass of the white dwarf and so on. And well, roughly speaking, this system looks like very heavy, strongly magnetized, rapidly rotating mass oxygen neon white dwarfs. So yeah, 5 minutes late. Right. どうしようか。I see. So anyway, so looks like yeah, and again, this is also model-dependent arguments, but we can argue how old this system is, and this system. Well, as I explained, this massive wind is produced by the carbon burning at the shell of the surface of the oxygen neon white dwarf, and that kind of burning it typically happens after the Kelvin Helmholtz time scale of the core shrinks, so the envelope tries to catch up and heat it up and burn. So the typical time scale for this happen is kiloyear, and actually after 1,000 years ago, there's a Chinese and Japanese history record that there's a bright, not so crazily bright, relatively dim type of transients recorded. That is called supernova 1181, and roughly speaking, kiloyears ago. And so now, including ourselves, people hypothesize this white dwarf formed through the merger of oxygen neon and carbon oxygen white dwarf. And at that moment, dim type of type 1A is observed by the ancient Chinese Japanese people. And actually, they compare the brightness with a Saturn or something. And maybe, well, as you can imagine, there are lots of uncertainty, but that's consistent with a dim type of type 1A, so-called type 1AX. That's not a complete explosion of the white dwarf, but a partial explosion of the white dwarf. So maybe the oxygen neon and carbon oxygen white dwarf merger, type 1AX, and KH contraction happen in kiloyears, and the strong intense wind start to blow. And that's what we currently detected. And if you believe this, then the event rate of this system, again, only one system, but the event rate would be like 10 to minus 3 years per galaxy. So it's quite high compared with for example, the required formation rate of FRB sourcing neutron stars. So maybe this is only partially account for the FRB-like neutron star. でももう時間がないですね。So we only have 3 minutes. Okay. So okay. GTF and so on start to discover. So question is how strongly magnetized and how fastly the collapsed object should be. And to answer that question, we have to know the pre-collapse magnetic field strength and rotation period. And thanks to the survey, we have good injection about the strongly magnetized heavy white dwarfs. And I will skip that later. So in the context of FRB, the question is when the collapse happens. Since as I said that the accretion-induced collapse typically have a time lag after the merger. It have a kiloyear. You have to spend a kiloyear to collapse actually happens. So the question is during that kiloyear, how the magnetic field and spin evolves. It's like a neutron star spin and magnetic field evolution arguments. So where they form. And how this is a rotation period versus magnetic field, how they spin down, how the magnetic field evolves, and at what point accretion-induced flux happens. And then you can roughly assume the flux freezing, and then you can argue how strong the magnetic field of neutrons are and so on. So to answer this question, again, we have to have a good knowledge about these kind of system. And as I explained, that just start to be obtained. So it's kind of good in a sense, good coincidence given the evolution of FRB community. And we are doing those kind of. And the last question is how this explosion looks like, and not only ourselves but some people have been discussing about possible supernova signature. So good. Hopefully we identify some looks like collapsing system, and then capture the moment that collapse and observe the supernova, and then wait, say, another 1 year and start to detect the FRB from the system. Then that completes the cycle of the story. And one important thing about accretion in these collapse is that they are relatively weak explosion, and ejecta mass is tiny, so the supernova property is quite different from the conventional supernova. And also, as you know, that the supernova property also can be affected by the central neutrons property. For example, if you want to have some strongly magnetized neutrons that explain the FRB, then that kind of strong magnetic field and rapid rotation can also make the supernova brighter. So you can play with. So this is the. Sorry, I'll stop soon. So this is no, just nickel explosion. So very dim. This is the AIC supernova. So short answer to the Uri-san's question is that if there is no energy injection from the central neutron star, it's very dim and fast. So even most up-to-date high cadence optical survey can miss that. And if we increase the B field and rotation, the supernova can be very bright. So this kind of property depends on the B field strength and the spin period. So if we start to detect them in the LSST ERA and so on, then we may start to catch the moment of formation. Okay, so sorry for spending more time, and I'll stop here.
Thank you, Kazumi. Is there any question from the on-site participants? Oh, yes, please.
Thank you very much for nice summary. So I have a naive question. I'm not familiar with accretion-induced collapse, but what's the difference between AIC and type 1 supernova?
Still, it's not settled down, but the main difference is the central white dwarf, oxygen, neon, carbon, oxygen. So if you have an oxygen, neon, white dwarf, then even though oxygen ignite, but the ignition happens in a very deep region, or more gravitationally bounded situation, then the released energy is not sufficient to explode the oxygen in white. So that's the difference. So carbon, in the case of carbon burns, and the energy is more efficient. So released energy is sufficient to explode the entire star. Yeah.
Thank you very much. I have a follow-up question. So in terms of the offset distribution, do you expect a similar distribution both for type 1A and accretion induced?
Well,
because I'm asking this because at the beginning of your slide, you showed the difference between defined population transient. And then, if I remember, FRB is similar to core collapse supernova. And then I wonder if it is, how different it is from the type 1 supernova.
So as I said, that well, although we have a lot of accreting white dwarf system and those maybe white dwarf binaries in our galaxy, but we haven't known which one is the massive oxygen neon white dwarf hosting system. So to do that, and we have excellent spectroscopy to nailing the only oxygen neon feature. And although you can use that the accreting white dwarf binary system distribution, but that may be biased or FRB population may have some bias, so that's a tricky part. So,
okay. Thank you very much.
Thank you. Are there any online question? We can have one quick question. If no, I have a quick question. So as I remember correctly, accretion-induced collapse have two kind of FRB scenario. One is that expecting FRB signal at the time of this collapse. And the other is the remnant, emission from the remnant. So you're mainly talking about the remnant scenario.
Still, it ejecta 10 to minus 3 solar mass ejecta. So I don't think it's not so easy. It's easy to produce FRB and soon penetrate through that kind of heavy ejecta. But still, well, compared with other conventional supernova, this system should be transparent to FRB, say, 1 week after the explosion, or 1 day or 1 month after the explosion. So in that sense, it's more, how to say, nice. If this is true, then we can soon try to start the FRB from that kind of strange type of supernova.
I see. Yeah. Thank you so much. Thank you again, Kazumi. Thank you.